So in today's video we'll be seeing how to query the processes in our system using the NtQuerySystemInformation function. So this function resides in the NtDrel and you can see the parameters here. The first parameter is system information class. So the type of system information you want to retrieve. Here we can see some of the types of system informations: basic information, code integrity, exception, interrupt, and you can see different types of system informations. And here this is what we need: system process information. So it returns an array of system process information structures, one for each process running in the system. So this is the type of system information we want to retrieve. And the second one is the pointer to a buffer where this function writes the information. And the third parameter is system information length. So we need to specify how much of this buffer can hold, and the return length is the actual return length of the entire structures. Suppose the process running maybe 200, so for after 1 second or 2 seconds maybe there are 5 more processes, so that's why this length will be varied, and we do not know how much length we need to pass. So that's why for the first time we will be passing a random number, and then it will tell us how much length is being returned, and we will allocate that much amount of length. So if you search for this NtAPI in crates.io, here we can see I have already imported this one. In cargo.toml file, import this NtAPI 0.4.0, and we should also import another Microsoft's implementation of Windows API in Rust, that is Windows Crate. So here in this we are going to use one structure called system process information that has the default attribute. So now if you go and to this documentation, you can search for NtQuerySystemInformation. Now here you can see different functions. So in the NtXAPI we have this NtQuerySystemInformation. So if you click on this first parameter, it will take you to a enum. This is a number, so let's first actually import all of this. So I have already imported this one, NtXAPI star, and here the system process information. So first what we are going to do is we are going to allocate some memory to hold all these structures. So we can use virtual alloc. So we are specifying the null address, so the OS will allocate for us, and the type is memcommit, and the protection type is read write execute. So the size, let's say 10,000 in hexadecimal bytes. So we want to say info length. So first we are going to allocate the 10,000 bytes in hex, and then we are going to write this function NtQuerySystemInformation. And if you click on this one, you can see the type is system information class. This is just a enum. So here we have the values. So if you want to retrieve the process information, you need to pass the number 5. So the 5 has been passed, and the second one is pointer to the buffer. So we can pass this one directory base address, and the system information length is info length. And return length, so what we are going to do is we are going to store the return length in this info length variable only. So ampersand mute info length. So this function overrides this variable value, specifying the amount of memory amount of size required to hold the structures. So expected U32 found U size. So okay, expected U32. Let's run this. So it's here, not here, as U size. Okay, so sorry for that, I did not see that red line. Okay, now we have called this function, and let's get the return value, and the return value is I32, which is a number. So if the number is 0, then it is success, otherwise it is failed. So let's go and print these values. And let's also free this region base address. Free type is 8000 IS to completely release. Yes, 8000 for memory release. So let's go and run this one. Cargo run release, and we can see the error is this one, signed integer, and it is not 0. So we are going to convert this one into the hex format, and let's nt status codes. Now search for this one, and here you can see status info length mismatch. So that means this 10,000 value is not correct. Now let's go and print the value of this info length here. Info length returned in info length. Now if we go and run this one, and you can see the 10,000 has been changed to some value. So this has been changed to some value. So this is the amount of size we want to allocate. So what we are going to do is, now we are going to write for infinite loop. So while true, we are going to call this function in an infinite loop until the result becomes 0. So we have declared a base address and we have allocated, and we are calling this function, we are printing these values. Now if this is wrong, we are going to free this one. So free this if res is equals to 0, then break. So the result is 0, then we need to break this loop, otherwise we are going to continue. And we need to allocate this one again. So base address is equals to, again use the virtual alloc to allocate this much amount of size, because this info length will be updated by this function, and we are going to allocate the new memory region with that length. And let's also say let mute tries is equals to 0, and if tries is equals to 5, break. So we are not going to try more than 5 times. Now you can print the base address. And you can also print the try value. So you are printing the result and info length and the tries. So cut this one, paste before this one. So we will see the result value. Now let's go and run this. And here we can see the first one is the something that result we have seen, status mismatch. Now it has returned this 7C2C8 length. Now we have allocated that much amount of data to this base address. Now the trace is 0 and result became 0, and the trace is 1 because we are breaking this when the result is 0. So the base address, at this base address we have the structures, system process information structures. So these structures, and these structures will also be followed by system thread information structures. So here we can see the number of threads value. So this structure will be followed by these structures and how these many number of structures. If the value is 5, then after this structure we will see 5 thread information structures. Okay, so we have the base address, and what we are going to do is we are going to declare a SPI, system process information structure default. Okay, both are same. It is trying to get from NtAPI crate, but here we have specified from Windows crate. So we have now structure ready. So we can call the function fill structure from memory. Base address as constant c void. Now this structure will be filled, so let's go and print this one. We are getting an error. Take 3 arguments, so we forgot the process handle, and we can use get current process. Now we are good to go. So let's go and run this one. We should see a structure. You can see the SPI structure and the next entry offset. So this is very important one. So the base address is this one and the next offset is 770. So if you add this value to the current SPI address, then you will get the next structure, that is next to process this structure. And number of threads we have 16, and image name, this is the Unicode, and the length is number of bytes in Unicode, and the buffer is a pointer pointing to that string. And we have other process usage details as well. Now let's go and fetch all the processes, and here they will tell you that the next entry, the last process entry, next entry offset is 0. So we have the structures of system process information. The last processes structures next entry offset will be 0. So that means we want to walk through these structures, and if you find a next entry offset value as 0, then that means that is the last process. So next entry offset is 0. So let's go and walk through all of this. Let's write another infinite loop. We are going to put the breakpoint, breaking expression. If SPI dot next entry offset is equals to 0, then we are going to break the loop. Otherwise, we are going to continue. Let's say let mute previous address is equals to base address. Now if you add base address plus SPI dot next entry offset, so that will give you the next address. Okay, as I size. Okay, now we have the next address, so we can again do the same. So let me copy this one, fill structure from memory. So we are filling the structure, the same structure SPI, and the now base address will be changed to the next address. Now you can print the entire structure. Now we need to forward this base address as well, otherwise this will be going into the infinite loop. So base address is equals to next address. Now after printing this one, we are forwarding into the next one. So I think we are good to go. So let's give it a try. So let's run this, and we can see so we can see all the processes information. We can also limit ourselves to printing only the juicy information or the information we want. So let's remove this one, and we are going to print next entry offset. So copy this, and we are going to print the process handle, and we are going to print the image name. So I think we are good to go. So spi.next entry offset, and the unique process ID and the image name. Now copy these three statements and replace with this one. Now let's run this. Now you can see all of these values. So we have stopped the loop whenever we see the next entry offset is 0. Now this is not very useful information. Because of this one, we need to parse this into a Unicode string. So for that, we are going to create a vector. Let's say let mute v1 of type u8. I think that is u16. So if you go to the Unicode string, you can see the type is u16 and the length is defined by this length. So you need to read this buffer up to these many bytes. So u16 is equals to vec, and I'm going to declare 0, and how many number of bytes we want to allocate to this array, that is defined by this length. So I can say spi dot image name dot length length dot 0 or no length as usize. Now we have declared an array to store the buffer pointed to by this buffer pointer. Now we can do read process memory and get current process, and the base address is going to be spi.imageName.buffer.0. So this gives the value, and to which buffer we want to override, that is this one, v1 dot as mute pointer, and the size we want to write is this one. So number of bytes we want to read, and we don't care about the number of bytes read. So now we are good to go. So what we are doing here is we are going to this location pointed by the buffer, and we are reading these many number of bytes. Here we can see the buffer is pointing to the address, and the length is 14 hexadecimal bytes. So from here onwards, if you read 14 hexadecimal bytes of u16 values, then you will get the string. Now we have the vector. We can simply let's say proc name is equals to string from UTF-16 RASI and specify v1, and we are good to go. We can print the process name instead of the image name, and let's also print a boundary line to make things a little bit easier to see. So let's run this, and okay, we got this null bytes. So we are getting these null bytes. So okay, now we got rid of this null byte. So here we can see the process name and the next entry offset and the process handle. So this is how you can use NtQuerySystemInformation function to retrieve the process information.